Welcome to EduAura students. I'm Divesh Chandra, your physics mentor. So in this section, we'll be discussing the previous year questions, PYQs. Here's the first question for you. Let a total charge 2q be distributed in a sphere of radius r with the charge density given by rho r equals k into r, where r is the distance from the center. Two charges A and B of minus q each are placed on diametrically opposite points at equal distance A from the center. If A and B do not experience any force, then option A equals 8 to the power minus 1 by 4 into r. Option B, A equals 3r by 2 to the power 1 by 4. Option C, A equals 2 to the power minus 1 by 4 into r, or option D, A equals r by root 3. This question was asked in JEE Main 2019, 12th April, 2nd session. Let's have a look at the solution for this. Now in this question, the key idea is that force applied by the sphere on the charge exactly cancels out the force applied by the other charge placed at the diametrically opposite point. So first, let's try to calculate the electric field at that point where the charges are kept, which is at a distance a from the center as mentioned in the question. So first things first, we have been given that the charge density rho varies as k into r. And also we have been provided that the total charge 2q is distributed in the sphere. So using this approach, we can calculate the value of q. How would we do that? We would consider an element. So essentially, we'll consider a hollow sphere, let it be at a distance r, and it has a thickness dr. So let us try to calculate this small charge dq on this spherical shell. It will be the surface charge density. It will be the charge density k into r multiplied by the volume of this hollow sphere, which is 4 pi r square dr. And let's try to integrate it from r is equals to 0 to r equals capital R. Now, in the question, it specifies that this is equal to 2q. So let's try to integrate this. You have k into 4 pi, which can be taken constant. You have r to the power 3 dr integrating from 0 to capital R. Now, when you integrate, you get 4 pi k multiplied by capital R to the power 4 by 4. Now, you can simplify this and you get pi k into capital R to the power 4. Now, according to question, that is equal to 2q. So, therefore, the value of k is 2q upon pi into R to the power 4. Now, in this case, we can calculate the electric field by this uniform surface at a distance a. How would we do that? We will apply the Gauss law. Let us consider a Gaussian surface at a distance a from the center. In this case, you have the Gauss law E dot dA integral for a closed surface, then this is equal to the enclosed charge upon epsilon naught. Now, you have E dot dA. Since the situation is completely symmetric, so you can treat that at every point the value of E will be the same, and that will be in the radial direction. So we can replace simply this with E multiplied by integral of dA, which will come out to be E multiplied by the surface area for this surface, which is 4 pi a square. Now that is equal to the enclosed charge in this. How much charge will it enclose? That will be equal again to integrating the surface charge density from 0 to a. And we do that by simply considering a thin shell at radius r and thickness dr. Again, we arrive at 4 pi r square dr multiplied by k into r, the charge density, and integrated from 0 to a in this case. And we get E into 4 pi a square equals k into 4 pi multiplied by a to the power 4 by 4. You can cancel out the 4 and you can cancel out a square from this. You can also cancel out pi. Now you can go ahead and replace the value of k that you had just calculated, which was 2q upon pi into r to the power 4 in this question. And when you do that, you arrive at the value of electric field, which is k a square by 4 epsilon naught. And finally, by substituting the value of k, 2q into a square upon 4 pi epsilon naught into r to the power 4. Now this is the value of electric field at a distance a from the center. To get the force on the charge, let's call that F1, which is the force applied by this charge distributed in the sphere on that charge minus q, which is placed on each ends. So that will be equal to q into the electric field. That comes out to be 2q square into a square upon 4 pi epsilon naught r to the power 4. And let us consider the repulsion force by the other charge placed at the diametrically opposite point. It will have a magnitude kq square by r square, where the separation in this case is equal to 2a. So that will be written as q square by 4 pi epsilon naught into 2a whole square. That reduces to q square by 4 pi epsilon naught into 4a square. Since we are talking in this question that the charges do not feel any force, so that means that both these forces, F1 and F2 in this situation, F1 being the force by the charge distributed in the sphere, and F2 being the force the other charge placed at the diametrically opposite point applies on the charge, they both must be equal. So let's equate F1 equals F2, and that gives us 2q square a square upon 4 pi epsilon naught r to the power 4 equals 1 by 4 pi epsilon naught into q square by 4a square. And on simplifying, you get 8a to the power 4 equals capital R to the power 4. So therefore, a must be equal to 8 to the power minus 1 by 4 into r. Now, if you match your options, option A is the correct answer to this question. Let's now go ahead and see the next question. 4-point charges minus q, plus q, plus q and minus q are placed on y-axis at y equals minus 2d, y equals minus d, y equals plus d and y equals plus 2d respectively. The magnitude of the electric field E at a point on the x-axis at x equals d, with capital D being very greater than small d, will behave as option A, E directly proportional to 1 by d, option B, E directly proportional to 1 by d cube, option C, E directly proportional to 1 by d square, or option D, E directly proportional to 1 by d to the power 4. This question was asked in JEE Main 2019, 9th April 2nd session. Let's have a look at the solution for this. First thing you should do is draw the situation very neatly, and as you can see here, the charges are placed clearly on the y-axis with separation plus a, with separation plus d and plus 2d for plus q and minus q, and now beneath that you have minus d and minus 2d for charges plus q and minus q. And you have to calculate the electric field at a point D, which is very greater than the small d which was used to measure the distances from the x-axis for the charges. Now, let us consider that these two charges subtend an angle theta 1 and theta 2. In this case, I am considering the minus q charge, which is at a distance 2d from the x-axis, subtends an angle theta 1 from the x-axis, and this charge plus q, which is at a distance plus d from the x-axis, subtend an angle theta 2. And it will exactly be the case for the other two charges on the other side of the x-axis on the negative y-axis, and those will also subtend an angle theta 1 and theta 2, as can be clearly seen in the figure. Now, if you notice, the situation is clearly symmetric. The electric field applied by the extreme charges minus q and minus q at a distance 2d, they both will give only the x component, because y component would cancel out. And that will be exactly the same for the plus q charges on the other ends at a distance d apart. Those will also cancel out. Just the fact of the matter is that for minus q charges, the electric field would be directed towards them, and for plus q charges, it will be directed away from them. So let's try to write the x component of all these electric field, because essentially the y component would cancel out. The x component would give us, let's call the magnitude of E1, let's call the magnitude of electric field by positive charges to be E1 and that of negative charges to be E2. So that gives you the net electric field in the x direction to be E1 cos theta 1 plus E1 cos theta 1, there are two of them, minus E2 cos theta 2 minus E2 cos theta 2. So essentially that gives you 2E1 cos theta 1 minus 2E2 cos theta 2. So now we can substitute the value in this case. For E1, you can substitute the value E1 equals KQ by small d square plus capital D square, and for E2 you can substitute KQ upon 2D whole square plus capital D square. And on substituting the value, you can also substitute the value for cos theta 1. Let's try to figure out cos theta 1. If you look at the figure in this case, then you can clearly see that cos theta 1 will be equal to capital D upon d square plus capital D square to the power half from the Pythagoras theorem. And similarly, cos theta 2 will be equal to d upon under root 2d whole square plus d square. So finally, if you substitute these values in the value of electric field, you get 2kd whole multiplied by d square plus capital D square to the power minus 3 by 2 minus 4d square plus capital D square to the power minus 3 by 2. Now you can take the denominator common as d cube. That gets you 2kq d upon d cube multiplied by 1 plus d square by capital D square whole to the power 3 by 2 minus 1 plus 4d square by capital D square whole to the power minus 3 by 2. Now, in this case, you have been given in the question that capital D is very, very larger than small d. So you can apply the binomial approximation that 1 plus x to the power n is equals to 1 plus nx. So when you do that, you can simply multiply this by the power, which is minus 3 by 2. So you get 2kq by d square on cancelling out the d's multiplied by 1 minus 3d square by 2 capital D square minus 1 minus 3 by 2 4d square by capital D square, and on simplifying it comes out to be 9kq small d square by capital D to the power 4. Now, in this question, it is very evident that the electric field is directly proportional to 1 by capital D to the power 4. And if you match the options, option D is the correct answer to this question. Let's now move on to the next question. 2-point charges Q1 root 10 microcoulomb and Q2 minus 25 microcoulomb are placed on the x-axis at x equals to 1 meter and x equals to 4 meters respectively. The electric field in volts per meter at a point y equals 3 meter on y-axis is, you have to take 1 by 4 pi epsilon naught equals 9 into 10 to the power 9 Newton meter square per coulomb square. You have your options. Option A, 63 I cap minus 27 j cap into 10 to the power 2. Option B, 81 I cap minus 81 j cap into 10 to the power 2. Option C, minus 81 I cap plus 81 j cap into 10 to the power 2. Or option D, minus 63 I cap plus 27 j cap into 10 to the power 2. This question was asked in JEE Main 2019, 9th January 2nd session. So let's have a look at the solution to this question. Let's try to first draw the situation diagrammatically, and you have been given that Q1 of charge root 10 microcoulomb is placed at x equals to 1. Let's place Q1 over here. And Q2 of charge minus 25 microcoulomb is placed at x equals to 4. So now you have been asked to calculate the electric field at a point on the y-axis 3 units above the origin, which is essentially 0, 3. So let's try to write the net electric field at this point 0, 3. If you notice from the diagram itself that the direction of electric field due to Q1 will be directed radially outwards towards this direction, and the electric field due to Q2 will be towards Q2 because it's a negative charge. So let's try to write the value of electric field in the vector form. We know that the electric field in vector form between 2 points of position vectors R1 and R2 can be written as KQ into R2 vector minus R1 vector upon the magnitude of R2 minus R1 whole cube. So essentially for this vector, the electric field due to Q1, let's try to write that. You have 2 points. This point can be referred to as 1, 0. So the position vector of this can be written as I cap plus 0 j cap. And this is located at the point 0, 3. So the position vector of this can be written as 0 I cap plus 3 j cap. So essentially, the vector directed from this point A to B can be written as vector OB minus vector OA. In this case, let's try to write it. It's going to come out to be 3 j cap minus I cap, which can be written as minus I cap plus 3 j cap. So essentially, the electric field at that point will be written as K into Q. The value of Q in this case is under root 10 microcoulomb. So let's try to write that K into under root 10 into 10 to the power minus 6 upon the magnitude whole cube. Now if you see, the magnitude of this vector is 3 square 9 plus 1 under root 10. So let's write that as under root 10 whole square multiplied by under root 10, which would ease us in the simplification, and multiplied by the vector R2 minus R1 gives us minus I cap plus 3 j cap. So this is the electric field of charge 1. So this is the electric field vector by Q1 at this point on the y-axis. Let's again try to write the electric field due to Q2, which will be again written as KQ into vector R2 minus R1 upon the magnitude of R2 minus R1 whole cube. In this case, if you calculate the vector joining Q2 and directed from this point on the y-axis, let's call it P and Q. So essentially, you are to write vector PQ. So going by the definition of vectors, vector PQ can be written as OQ vector minus OP vector. In this case, OQ is R2 and OP is R1. So therefore, OQ vector, as we know, can be written as simply 4 I cap because it's situated at x equals to 4, and OP vector as plus 3 j cap. So therefore, it comes out to be 4 I cap minus 3 j cap. Now, when you substitute the values, here you have KQ, the value of Q is 25 microcoulomb. So let's write that as 25 into 10 to the power minus 6 multiplied by the vector PQ. It comes out to be 4 I cap minus 3 j cap and divided by the magnitude of the vector whole cube. So that gives you the magnitude, which is 5 in this case. So let's try to write that as 5 square into 5, which will help us in simplification. So to find out the net electric field, you need to make the vector summation for vector E1, the electric field due to Q1, plus vector E2, the electric field due to E2. Let us substitute the values that we had just calculated. For E1, it comes out 9 into 10 to the power 2 multiplied by minus I cap plus 3 j cap. And for E2, you have 18 into 10 to the power 2 multiplied by 4 I cap minus 3 j cap. And when you simplify this, you get the net electric field vector as 63 I cap minus 27 j cap into 10 to the power 2. And when you match your options, option A is the correct answer to this question. Let's now move on to the next question. Charge is distributed within a sphere of radius r with a volume charge density rho equals a by r square into e to the power minus 2r by a, where capital A and A are constants. If Q is the total charge of this charge distribution, the radius r is option A log of 1 upon 1 minus q by 2 pi a capital A. Option B, A into log of 1 minus q upon 2 pi a capital A. Option C, A by 2 into log of 1 minus q by 2 pi a capital A. Or option D, A by 2 into log of 1 upon 1 minus q by 2 pi a capital A. This question was asked in JEE Main 2019 9th January 2nd shift. Let's have a look at the solution for this. Now in this question, you have been specified the variation of density as radius changes. Now in this question, you have been specified the variation of charge density, volume charge density with the distance from the center. So if you are to calculate the total charge in this, you must perform integration by dividing this sphere into small strips of hollow spherical shells. So let us consider a spherical shell at a distance r and of thickness dr. So in this case, the small charge dq on this can be written as the density rho multiplied by the small volume for this. Now, we can almost consider this charge. So the question specifies the value of rho to be varying with r as a by r square into e to the power minus 2r by a, and multiplied by the small volume of this spherical shell, which is equal to 4 pi r square, the surface area, multiplied by the thickness dr. And if we integrate this from r equals to 0 to r equals capital R, we will get the total charge on the sphere, and the question specifies that to be equal to capital Q. So let's equate it with that. Now let's perform our integration. You can go ahead and cancel out the r square. You can treat a into 4 pi as constant, which will come out of the integration. It will give you a into 4 pi multiplied by e to the power minus 2r by a into dr. So integration will essentially be performed on this function. Now, if you know the integral of this e to the power x function, it is simply e to the power x. But in this case, you see that e to the power r is multiplied with a factor minus 2 by a. So we'll have to account that in the integration by dividing it from the final integral. And that will give you a into 4 pi multiplied by e to the power minus 2r by a divided by minus 2r by a. And we'll have to substitute the limits r equals to 0 and r equals to capital R. So in this case, if you clearly see, this comes out to be equal to 4 pi a into minus a by 2 into e to the power minus 2r by a minus e to the power 0. So essentially, it comes out to be minus of 2 pi capital A multiplied by small a into e to the power minus 2r by a minus 1. And if you simplify this, you get capital Q is equal to 2 pi a small a into 1 minus e to the power minus 2r by a. So from this, you can easily find out the value for capital R, which comes out to be a by 2 into log of 1 upon 1 minus capital Q by 2 pi a capital A. And if you check your options, option D is the correct answer to this question. Let's go ahead and see the next question. 3 charges plus capital Q, Q and plus capital Q are placed respectively at a distance 0, d by 2 and d from the origin on the x-axis. If the net force experienced by capital Q placed at x equals to 0 is 0, then the value of Q is option A plus capital Q by 2, option B plus capital Q by 4, option C minus capital Q by 2, or option D minus capital Q by 4. This question was asked in JEE Main 2019 9th January first shift. Let's have a look at the solution. Now the question specifies that 3 charges are placed on the x-axis, with the first charge capital Q being placed at the origin, the next charge small q being placed at d by 2, and the next charge also plus q placed at a distance d. So now the question also specifies that the force applied on this capital Q charge, which is placed at the origin, is equal to 0. So essentially, let's try to write the net force on this charge capital Q at origin by the charges small q placed at d by 2 and plus q placed at d. Let's call them F1 and F2. So in this case, F1 will be equal to K capital Q into Q divided by d by 2 whole squared, and F2 will be equal to K capital Q square upon d square. Now, in this case, we have not yet assumed any sign for small q. Let us, for simplification, keep it positive. It will turn out later in this section that it will be a negative charge, because you can clearly see that the plus q charge would repel this. Then in order for this charge to not feel any force, q must attract it towards itself. Only then it can be possible. So let's go ahead and write the net force simply F1 plus F2 to be equal to 0, and that gives us K capital Q small q upon d square into 4 to be equal to minus K capital Q square upon d square. And when you simplify, you can cancel out the d's, you can cancel out the value of one of the q's. So small q from this comes out to be minus capital Q by 4. So if you compare your options, option D is the correct answer to this. Let's now go ahead and see the next question. A uniformly charged ring of radius 3a and total charge q is placed in xy plane centered at origin. A point charge q is moving towards the ring along the z-axis and has speed v at z equals 4a. The minimum value of v such that it crosses the origin is option A, root 2 by m into 1 by 5 q square by 4 pi epsilon naught a whole to the power half. Option B, root 2 by m into 4 by 15 q square by 4 pi epsilon naught a whole to the power half. Option C, root 2 by m into 1 by 15 q square by 4 pi epsilon naught a whole to the power half. Or option D, under root 2 by m into 2 by 15 q square by 4 pi epsilon naught a whole to the power half. This question was asked in JEE Main 2019 10th April first session. Let's have a look at the solution for this. Now, if you look at the question, you can see that initially the point charge is kept at a distance 4a, and you have to provide it a minimum velocity so that it crosses the origin. So essentially, the difference in the energy, the potential energy from this point, which is x equals to 4a, and the point which is at the center, at the origin, this difference must be provided to the point charge in the form of kinetic energy. So let's try to write the potential difference at these 2 points. Let's call them P, which is at a distance 4a, and let's call the center C. So the potential at P will be equal to kq upon radius r square plus x square. In this case, the radius r is equal to 3a and the distance is 4a. So Vp comes out to be kq by 5a. Also in this case, the potential at the center will simply be equal to kq by the radius, which comes out to be kq by 3a. Now, the difference in potential will be Vc minus Vp, essentially kq by 3a minus kq by 5a, and the potential energy difference will be equal to this potential difference multiplied by the charge, that comes out to be 2 by 15 into kq square by A. Now, as we have already discussed, that this energy must be provided with a value. Now, as we have discussed, that this energy must be provided to the point charge in the form of kinetic energy. So therefore, for the minimum value, we must provide at least this much amount of kinetic energy, and we can go ahead and equate this potential energy difference with the kinetic energy that must be provided equal to half mv square, and we can calculate the value of v square, which comes out to be 2 by m into 2 by 4 pi epsilon naught into q square by 15a. So therefore, v will be equal to under root 2 by m into 2q square by 15 into 4 pi epsilon naught a whole to the power half. And if you compare your options, you clearly see that option D is the correct answer to this question. Let's now move on to the next question. Assume that an electric field E equals 30x square I cap exists in space. Then the potential difference VA minus V0, where V0 is the potential at the origin and VA is the potential at x equals 2 meter, is option A 120 joules, option B minus 120 joules, option C minus 80 joules, or option D 80 joules. This question was asked in JEE Main 2014. Let's have a look at the solution to this. Now, going by the definition of potential difference, we can clearly say that VA minus VO will be written as minus E dot dx, integrating from R0 to RA. In this case, you have been given that E is 30x square, so we'll integrate it from x equals to 0 to x equals to 2 in this case. And when you do that, you clearly see that VA minus VO will come out to be minus 80 joules. And if you compare your options, option C is the correct answer to this question. Let's have a look at the solution to this. A charge Q is uniformly distributed over a long rod AB of length L as shown in the figure. The electric potential at the point O lying at a distance L from the end A is option A Q by 8 pi epsilon naught L, option B 3Q by 4 pi epsilon naught L, option C Q by 4 pi epsilon naught L ln 2, or option D Q ln 2 by 4 pi epsilon naught L. This question was asked in JEE Main 2013. Let's have a look at the solution. So in this case, you have a rod of length L, AB, and you have been given that a charge Q is uniformly distributed over this surface. Now, you have been asked, also in this question, you have been asked to calculate the electric potential at the point O, which is also a distance L from the end A of the rod. Let's go ahead and try to do that. We'll have to break the rod into various segments. Let us consider a segment, a small length dx at a distance x from O. And let's try to write the potential due to this small charge. This small charge dq will be equal to the charge per unit length multiplied by the length. And since we are talking about a uniform rod, so this will simply be equal to q upon L multiplied by the length, which is dx. So now the potential at this point will simply be equal to k into dq by x. Let us now substitute the value of dq in this. The small potential dv can be written as k into q by L into x dx. Now, to find out the potential for the entire rod, we have to add all of the potentials for each of the segment of the rod by integrating it from the end A to end B. Let's do that. The left end of the rod, x will be equal to L, and for the end B of the rod, x will be equal to 2L. So, we can go ahead and integrate this. It will be kq by L into integration 1 by x dx, which will come out to be ln of x and when you substitute the values L and 2L, you'll be getting KQ by L into ln 2 by 1 by applying the properties of logarithm ln b minus ln a equals ln b by a. So, as you clearly see, final answer comes out to be q by 4 pi epsilon naught, substituting the value of k in this, multiplied by 1 by L into ln 2. So, clearly you can see that the final result comes out to be for k 1 by 4 pi epsilon naught multiplied by q upon L into ln 2. And if you check your options, option D is the correct answer to this question. So let's now move on to the next question. Shown in the figure is a shell made of a conductor. It has inner radius A and outer radius B and carries a charge Q. At its center is a dipole P as shown. In this case, option A, surface charge density on the inner surface is uniform and equal to Q by 2 upon 4 pi A square. Option B, electric field outside the shell is the same as that of a point charge at the center of the shell. Option C, surface charge density on the outer surface depends on the magnitude of the dipole moment P. Option D, surface charge density on the inner surface of the shell is 0 everywhere. This question was asked in JEE Main 2019 12th April 1st session. Let's have a look at the solution to this. Now you have a conducting spherical shell like this, and inside of it is a dipole placed as shown in the figure with dipole moment pointing upwards. So that means that the negative charge will be placed here and directed towards the positive charge will be the dipole moment vector. So when you place a dipole inside of a conducting shell like this, what would happen is that the free electrons of the conductor would realign. Inside of it, all the electrons would come together to give a charge distribution like this, and on this side, positive charges would align. So essentially, in this case as well, if you notice that the net charge distribution is 0 because dipole has same charges, and in the question you have been provided that the conducting shell already carries a plus q charge, so that whole plus q charge will still be distributed on the outer surface like this. So if you go ahead and try to calculate the electric field at any point P outside that, you can do so by considering a Gaussian surface in the form of a sphere, and that would give you the electric field to be equal to kq by r square, which is exactly the same as that of a point charge kept at the center. So let's compare the options. Option A tells you that the surface charge density on the inner surface is uniform, which is clearly not the case. You can clearly see in the figure that in the inner surface, the charge distribution will be half will be negative and half will be positive. For option B is the correct one. Option C, surface charge density on the outer surface depends on P. It's clearly not the case. If you go ahead and change the orientation of this dipole, the outer charge density will still remain the same. Option D, surface charge density on the inner surface of the shell is 0 everywhere. It's clearly not the case. There is some charge density due to the alignment of the free electrons. So among these, only option B is the correct one, which is the correct option for this question. Let's now move on to the next question. A solid conducting sphere having a charge Q is surrounded by an uncharged conducting hollow spherical shell. Let the potential difference between the surface of the solid sphere and that of the outer surface of the hollow shell be V. If the shell is now given a charge of minus 4Q, the new potential difference between the same two surfaces is option A, minus 2V, option B, 2V, option C, 4V, or option D, V. This question was asked in JEE Main 2019 8th April 1st session. Let's now look at the solution for this. So as you can see that in this question, initially when the shell encloses charge Q, so the charge distribution due to the induction of the charges will be as can be clearly seen in this figure. The outer surface will have plus Q charge, the inner to that will have minus q, and then again the inner surface will have plus q charges. So you can go right ahead and calculate the potential at A, which will be kq by A plus k into minus q by B plus kq by B. Also, you can calculate the potential at B, which will be kq by B plus k minus q by B plus kq by B. So, the potential difference comes out to be kq into 1 by A minus 1 by B. Now, in the question you have been given that the potential difference is equal to V, so you can go ahead and equate these two, kq into 1 by A minus 1 by B equals V. Now, the question also tells you that after giving a charge minus 4q to the outer shell, the potential difference will be the same as V. So let's go ahead and give the outer shell minus 4q charge, and the potential difference comes out to be kq by A plus k into minus 4q by B minus kq by B plus k into minus 4q by B, and this also comes out to be kq into 1 by A minus 1 by B, which is equal to V in this case from the previous equation that we had already derived. Hence, we clearly see that the potential difference does not depend on the charge on the outer sphere. Therefore, the potential difference would remain unchanged, which will be equal to V. So, if you compare the option D is the correct answer to this question. Hope after these examples, you are now feeling increasingly confident and can attempt any situation or problems of these topics on your own. Keep learning and keep watching EduAura. Thank you.